Right, so today I would like to discuss the spherical coordinate differential element. Now, that is a mouthful, isn't it? What we discussed in the last video was the polar coordinate, or the 2 videos ago, we discussed the polar coordinate differential element, such that if I have my polar coordinate, the circle, right, that's the general polar coordinate with my r and my theta, then I can kind of draw it out here, and then here I have my differential element here, where here I have my d theta, and here I have my dr, right? So what we want to do in this video is expand this to the spherical coordinate differential element. So that's going to be like a 3D version of this using this sphere, where we have, if you remember, we have our different angles. We have our theta that sweeps that, then we have our phi that sweeps that, then we have a rho that goes out to there, and then it models our coordinate. It can model any coordinate that we want. So today we want to derive that integration differential element, which we kind of touched on in the spherical coordinates video, but I want to do it with the Jacobian. And then I just want to kind of briefly touch on everything we've covered in this unit, because this is our last video of the unit, and multivariable integration is something that we will be using a lot in the next unit of vector calculus. So the transformation for spherical coordinates goes like this. If you remember, we have x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine theta. The physicists sometimes mix up the r and the theta. I like to use this transformation personally, when I'm in physics. Sometimes I get a little bit messed up, but it's fine. So we have our transformation. Now what we need to do is we need to use the Jacobian. So previously we defined the Jacobian as a 2x2 matrix, but in reality we can define it as an n×n matrix. So what we do is we have a matrix where I have D U of x, and then we keep on going with the x components to d u n of x, and then we keep on going here all the way to d u of x n, all the way over to d u n of x n. So you're going to have multiple variables, and I could probably define this a little bit more neatly. If I want the ijth component of the Jacobian matrix, then the I will be the column and the j will be the row. Then I can, the I will be the row and the j will be the column. So the ith column, we're taking the partial derivative with respect to the ith unit, or the jth unit, or the jth transformation variable with respect to the ith component. So we just have dx sub I over du sub j. So that's how we can define it using just that index notation, which might be a little bit confusing, but it might be easier to visualize it like this. Anyways, we can use a 3x3 case for the transformation using rho theta phi from x, y, z. Anyways, what we get is, and remember we take the magnitude of the Jacobian. We don't want the positive or the negative, or we don't want the negative, we want the positive. So we take the magnitude of the determinant. So we take the determinant, and we need to take all of these derivatives. If I take the derivative of x with respect to rho sine phi cosine theta, then with respect to next variable theta, negative rho sine phi cosine sine theta, and with respect to phi, rho cosine phi cosine theta. And take the y derivative with respect to rho cancels, then rho sine phi cosine theta, rho cosine phi sine theta. And finally for the z, I take the rho out, cosine phi. With respect to theta, there's no theta dependence, that goes to 0. And then finally, if I take it with respect to phi, I get negative rho sine phi. Okay, now how do we take the determinant of a 3x3 matrix? Now what we do is we take this guy here, and then we multiply it with the determinant of this guy here, and then we add this guy here times the determinant of this guy here, and then we subtract this guy here multiplied with the determinant of that guy there. So we're ending up taking 3 determinants now of 3 2x2 matrices. So we take the last column. It doesn't really matter which column or which row you decide to be this guy here, but it will all end up the same. So what we do is we will use this just because we have a 0 in this, so we'll use this last row. And then the other 2 rows, you form the matrices out of the columns that are not being used, right? So what we will get when we take all of these determinants, something very messy. We get the absolute value of cosine phi times, so we take this, times determinant of this here, negative rho squared sine phi sine squared theta minus rho squared sine phi cosine squared theta. And then we do this term cancels because we've got a 0 here, so that's not going to matter. So now we need to go to this term here. We got negative rho sine phi, and then we subtract, times rho sine squared theta cosine squared phi plus rho sine squared phi sine squared theta, and absolute value. We can simplify this. We get absolute value of rho squared sine theta cosine squared phi minus rho squared sine phi sine squared theta. Or sine squared phi. Finally, we get absolute value of negative rho squared sine phi. And of course, absolute value with the negative cancels, so we get positive rho squared sine phi. So this is the result that we expect. This is the result that we have been getting when we define the spherical coordinate system. Anyways, if I want to take the integral, the triple integral, over a coordinate valued from x, y, z over volume, then I get the integral over a new region, likely a circle shape, of f of x, y, and z transformed into these spherical coordinates times rho squared sine phi d rho d theta d phi. Okay, so that is a long-winded derivation for the spherical coordinate system and its differential element by proof of the Jacobian matrix. Anyways, what I would like to do now is just briefly touch on what we have learned over the last unit. Again, very important to review this stuff. So, first off, we have discussed the idea of a double integral, taking the idea from a single integral of f dx over to a double integral of f of x and y dA. So what that meant for us is it not only meant more complicated functions and being able to find the volume of something, it also meant being able to be more generalized with the regions that we choose. Instead of dealing with simple portions along an x-axis like we did in single variable, now we can choose any region on a plane, right? Then what we did is we looked at all of the applications that we could use. We could use a moment of inertia, we could use center of mass, and of course that's all applicable for triple integrals too, if I want to find the center of mass or moment of inertia of a volume. And then we discussed the alternative coordinate system, polar coordinates, double integrals and polar coordinates. How can we make that work? How can we transform, and how can we use that to make our lives easier when performing these iterated integrals, right? Then after that, we moved into the idea of a triple integral. So we went further to the idea of a triple integral of a function over a volume, right? And we discussed that in all of the coordinate systems, the rectangular, the spherical, and the cylindrical coordinate systems. And we could have taken this further. We could have taken this to 4 dimensions. We could have taken this to 5 dimensions. We could have taken this to n dimensions. If you take general relativity or relativistic quantum field theory, you will be dealing with 4-dimensional integrals, of course, because you have space-time. So you have a time dimension and then 3 space dimensions. So you'll need to do quadruple integrals, which may seem complicated, but again, everything we've learned is generalizable. Finally, we discussed how we can make our lives easier by choosing which regions we can use by use of the Jacobian matrix, making our integrals easier by expanding the substitution rule so that we can take integrals of more complicated functions that might otherwise not be able to be integrated. So the point of this unit was to get our bearings with the methods for double integrals and triple integrals. Now, the reason for this is first because it's important on its own, but also along with the partial derivatives unit, these two units were a preparatory unit for our next unit, which is vector calculus. Now, the multivariable calculus is very important, but its real use is vector calculus. Vector calculus is what is extremely applicable in our everyday lives. If you think about weather meteorology, everything can be modeled by a vector field. Fluid flow can be modeled by a vector field. Quite a lot can be modeled by a vector field, and it's very important that we discuss these multivariable integrals and partial derivatives before doing that, just because it will be extremely important in the future. So in the next video, we will introduce the concept of a vector field, and then we will move on to line integrals. So thank you for watching. We'll see you then for our first video of Unit 5.